Now we are going to have something else. Now we'll come back a little bit to, again, an application that, let's say, the public sector has. That taxation, subsidies, seems like boring stuff, but you can also make them better. So we have Martin here talking about how to help large populations preserve privacy with zero knowledge.
Hello. Well, I don't know about large populations, given that it is Estonia. But yes, I will be talking about a use case that we did that was inspired by the Estonian EV subsidy rules. So this was a law that was in effect previously, well, at the time that we did it. And for those of you who don't speak Estonian, this is a subsidy towards buying EVs that has certain terms to it. One is that over 4 years, the car has to have driven 80,000 kilometers. Two is that 80% of it has to be within Estonia. And there's an extra requirement for renewable energy, but that is out of scope. For us, we're focused on the fact that how can you guarantee that people do actually drive 80,000 kilometers and 80% of it in Estonia, and do it in a privacy-preserving way. First, let's look at what they actually did. So the cars could be installed with GPS trackers. There was an opt-out for it, but the default way was that you would install a tracker which had the GPS module turned off. This was a special piece of firmware that was made for this purpose, and it allowed them to turn on or off the GPS module at will, and it was left off. I think on the user's request, if they also worked with were a customer for the company who provided the GPS modules, you could also get actual find my car features. But yeah, only the odometer and the location of the current country were transmitted to the service provider. However, this is still a bit of an issue, given that you do only transmit the odometer and the country. However, I have no guarantees that you don't turn the GPS tracker on, and this metadata still allows you to do some habit tracking, right? You can see when my odometer increases versus not, and that lets do some pattern analysis. So how can we do this better? We were asking this as we were, getting involved in the zero knowledge space more seriously, and I'll have to talk about what we were doing, because this project is a bit of you have to create a sandwich. You first have to create the world. So this is us creating the world, and then we'll make the sandwich. So we were members of a DARPA project called CIV, which was which really furthered a lot of zero knowledge adoption, specifically in situations where Web3 is not interested. So larger proofs. Web3 also does non-interactive proofs mostly. So a lot of these were interactive proofs, and really getting the gate count down, or like the nanoseconds per gate down. So what we did in this project was that we created our own programming language for creating zero knowledge proofs. This is the arithmetization process that was in an earlier talk, which is where you have the problem that you need to solve. How do I actually get to a zero knowledge proof of it? And again, our emphasis was on real data sizes. So we wanted to do something that wouldn't fit on a blockchain. And it outputs this intermediate representation that other protocols can ingest. So when you're designing a language for zero knowledge, one aspect that you can decide is like, do you want to make this as easy as possible for the programmer, or do you want to, well, not make it as hard as possible, but give them a lot more tools? Like, because it's very difficult to, have this best of both worlds option where you have all of these tools, but they're also very easy to use, right? So, and we went with the route of, we will give the programmers as much flexibility as possible to do everything they need to do, to be as efficient as possible, because the zero knowledge protocols, they're, I guess you heard Janno mention multiple times that the prover needs to get faster. The protocols were just like, in terms of computational power, they're not very strong right now. The ZK VMs, I don't know their current clock speed, but at the time of this, their clock speed was best measured in kilohertz and megahertz. So in a way, it feels like going a bit back in time, because you have to reinvent a lot of primitives, and you have to do it in a way where like you don't have too much computational power. And this type system allows us to do this. So we have these 3 dimensions, which is the actual data type, and then you have the stage and you have the domain. The stage marks whether if this is an off-circuit or on-circuit data type. On-circuit data types are things that are actually executed in the zero-knowledge proof in the end. Off-circuit ones are kind of in your head. So for example, I could take, as I'm writing this zero-knowledge proof, I might want to take some variable, calculate something else based off of it, while not revealing it, or not even involving it in the interaction with the other party. I'll do some in-the-head computation, and I put it back into the circuit, for example. That's something that where you take something off-circuit for a while, you do some off-circuit calculations, and then move on. The domain is for data visibility. So for example, if some piece of data is either public or only visible to the prover, or visible to the prover and the verifier. So here we have this triple of uint_n pre-prover, and this marks a integer, well, unsigned integer, modulo n, and it's pre as in it's off circuit, and it's at prover, meaning it's only visible to the prover. So these kinds of triples are all over the code base. We allow for branching on stage and domain, so that you can write the code very polymorphically, so that you can do polymorphism over both the stage and the domain, right? So I'll show you what that means in a code example. But before I get to that, I want to also mention another thing about the stage. So when I mentioned taking something and calculating in your head, this is a crucial technique actually in creating these zero-knowledge proofs. So because you want to do as little work as possible in the actual proof itself, you want to, well, you cut every corner you can. So insofar as you don't make things insecure, obviously, but for example, if there are some equalities that can be one-sided equalities, you'll do it. And one of the things you can also do is, instead of calculating a function, consider calculating, or instead of implementing the function, implement the inverse of the function. So for example, here if I have x, and I call f on it, I get f of x. Well, this is normal. the normal way to implement this. However, if my function, for example, is taking the square root, then, well, taking x, calculating the square root of it, the square root function is not so trivial. So you would have to do quite a bit of work in this step to get f of x. However, I could just take x, right, and then I could just calculate it in my head. So for example, like I have this x, I go off circuit where computation is fast because I don't do any zero knowledge things. So I calculate what the square root would be, right, and then I just put it on the circuit. And then obviously the verifier has no reason to trust this thing. Like I just put some value onto the circuit that it has no idea what it is. But if you compute the inverse of the value, inverse of the function on that value, so in our case, the inverse of the square root, so I just square f of x, maybe I get x, and then I just check, did I actually get x back? If I did, then the verifier can accept that the pre-image must have been f of x, right? And then by only implementing the inverse, I can use the function. However, this is very tricky because it is very easy to under-constrain. In this example, for example, with the square root, 10 times 10, if you're doing modulo 13, is 9. Maybe the verifier expected that it would have been 3, right? So you need to, if the only acceptable answer in that situation was 3, then you need to make sure that the number is like less than that the output is strictly smaller than the input. All right, and here's our example of Zeki secrecy. So this is super polymorphic, right? So we have a function called square root fixed. This here we have a parameter. So here we're saying that we're polymorphic over the field. So we just have a field n, and this is a natural number. We have a stage that's just $s, that's completely generic, and so is the domain, right? And then here you can see that in our code we have that if the stage is post, meaning that if we're actually, if we need to compute something for to put it on the circuit, then we do a certain thing, and otherwise we do this other branch. And we also have branching on the domain as well. So for example, there is this thing here that we would only need to check if the data type is prover. And the programming language then, like if I write in this language and I output, then I get an intermediate representation. So this is basically that arithmetization where I just get, I would get my field elements and my operations that I do on those field elements. And this we've been able to integrate with a lot of different backends. So we are able to use VLE-based zero knowledge proofs. So these are interactive. So tired mac and cheese and EMP. We can do MPC in the head and VLE in the head with that are like non-interactive. And then CirCom is another intermediate representation that is widely used in the Web3 space. And then we have additional features like function gates and field switching, which allows us to conserve either memory during runtime or not be locked into only one field on execution. So now that we have this, we have the universe, so now let's make the sandwich. So if you'll remember, we needed to make sure that 80,000 kilometers is driven in Estonia, 80,000 kilometers is driven and 80% of it within Estonia. So the proof that we generated is such that we first approximated Estonia with circles, Why circles? Because it's really easy to check if something is within the circle. It's just, distance from a certain point. So we took the GPS coordinates, we put them into an XY plane, and then given a coordinate trace, which has to come from some sort of trusted source, because, well, like a verifier couldn't accept just any coordinate trace, right? They have to have reason to believe that this coordinate trace is valid. But if this does come from a valid source, then the first thing you do is check the validity of the inputs. The second thing you do is find the total path length and the path length that is within the bounds. And then at the end, you assert that they're within the parameters. Because we wanted to do these large proofs that are actually practical, so we needed to be roughly within realistic performance constraints. So one thing is also that because of the design of the zero knowledge proof, it cannot leak anything about the length of your trip, for example. The number of coordinates is fixed. And this avoids, leakage of the activity patterns, for example. If you report your yearly driving, this would be like the coordinate amount would be set, and this would be the 43,200 coordinates per year is what we're estimating, because it's the average amount of driving that a person would do is about 1 hour a day, and the polling rate of 2 coordinates per minute seems to be pretty standard, or at least like in the tracking of fleet vehicles. So, input validation. I've been given some coordinates. Why should I be able to, me as the verifier, why should I accept them as a valid input? The coordinates should be signed, of course, but then, the signature has to also be checked. It can also luckily be checked outside of zero knowledge. So for example, if you send me signed coordinates, I can check the signature of the coordinates, and then I will have the hash of the coordinates. And then under ZK, I only hash the coordinates, and I don't need to do signature verification, because I already know that the hash is a legitimate hash for them because of the signature check that I did out of bounds. And we used Poseidon as our hash function for this, because we found that SHA-256 is just not practical in the zero knowledge environment for us, because if you are dealing with field elements that are not F2, then every time you would need to get this bit representation, you need to check that the bit representation is accurate, and only then can you do some bit manipulation. And that is just so much overhead that in this flame graph you see, this is a version where we use SHA-256, and this purple line shows that almost the entire duration of the program is spent hashing. So the rest of the program is like here in the margins. Versus when we switched over to Poseidon, which unlike SHA-256 doesn't do bit operations, it does field element operations, and that avoids this. We get much less time spent on hashing. And then, of course, we had to implement Poseidon in ZK secrecy, which is also a fun test that, of the language's general programming capabilities. And it also allows us to implement Poseidon for every field, because Poseidon is field specific. So once I have the inputs validated, then for each coordinate, I need to compute if it's contained within the circle and the distance to the previous coordinate. To do this accurately, we had to add support for fractional numbers, and this has a lot of witness expansion tricks for performance that I sadly cannot go into, because those get a little bit too dry. And then, this is basically just like summing all of the distances together, but it takes a lot of work to get it actually efficient. Now, before I show you the actual demonstrator, I want to address that we also did a version of this where instead of checking, the terms of the subsidy, we also looked at a very popular use case, which would be a highway tax. So, for example, Tallinn-Tartu is outlined there. So we want to show that I could prove that I have only driven d kilometers along a highway. So I would have like this, I could do this like per trip, so I can show that I only, drove this many kilometers on the highway, and then I could be taxed accordingly or something. And for this, we represented the highway as line segments and added a little, some margin on the sides, and then we created triangulation of the rest of the map. And then instead of checking if something is within the bounds of the road, we check if they're within the other surrounding triangles. And if they are, then we remove that from the sum. Now, the actual EV demonstrator itself, this is the sketch of it where we have a GPS logger. So this would be a device that's embedded within the car. For this, we use the Raspberry Pi, and we assume that this is either tamper-proof or tamper-evident, so that a person could. So we have some kind of reason to trust these coordinates because if the car's owner were to manipulate this, then it would be evident on the device. This logger then sends the coordinates and the signature for the coordinates to the prover, which would, in our case, was just an Android phone. And this prover contains in it our app that runs our part of the compiler and the zero knowledge protocol library. So in this instance, we used diet mac and cheese. So we packaged our, a part of our compiler along with their zero knowledge library. We put that all into WebAssembly, and then we were able to use the phone as the prover, and then just the x86 computer as the verifier. So the prover just sends the signature, and then they initiate the protocol to run the zero knowledge proof. I think I would probably be out of time if I went into that. So for the demonstrator, you can see here, this is our verifier, this is a battery bank. Our phone would be the prover here, and this would be the device that is embedded in the car. So important to note here, unlike the existing, the actual, the government solution that went into practice, this alternative would not have the coordinates ever leave your phone, or and it would also have no ability for it to do so, right? Because in the previous GPS tracker could be perhaps turned on. In this one, no, the Raspberry Pi here could perhaps be even a completely offline device, so that you have this tracker in your car that is completely offline, and then it sends out these signed coordinates, and then these coordinates only go to your phone. And when you launch the zero knowledge proof, the coordinates never leave your phone. And before you initiate the proof, you also get to see the coordinate trail. So this allows you to, look at your data and have an idea of what it is you're initiating. So, for example, otherwise you would not be able to see if this device in your car is even working properly, but thanks to this you can. The performance that we got is actually, I think, relatively realistic. So on a Pixel 5a, a single trip's proof takes 13 seconds to run. A month is 2 minutes, and a year's worth of coordinates is 10 minutes. And we also tried to have the pi as a prover, and that would be a case where if you wanted to bundle everything into one device that both logs and then proves, then because the Pi 5 has a hardware AES, this makes it quite efficient because, like, you know, a month takes 23 seconds to prove, and a year takes less than 3 minutes. I think if this was to go into actual production, I think you would get more similar performance to Pi 5 than the test we have here, because the hardware AES is really a key driver of performance here. So for example, here you can see the Pixel 4 versus Pi 4 versus Pi 5 performance difference. And it's a very large jump from 122 seconds to 23 on Pi 4 versus Pi 5. And that's just entirely because Pi 5 has hardware AES and Pi 4 does not. The year trip did not even run on the Pi 4. And hardware accelerated AES is there on the phones, but we were not able to access it because it's not available in WebAssembly. So if we were to take the engineering time and make a native application, then we would be able to have similar performance to the Pi 5. So I think it was a fun project, and I think it's actually, you know, this is the kind of thing that I would like to see actually put into practice, because I think the technology is starting to be there. Yeah, thank you.
One question, if there is one. There is a Artyom in the first row.
Have you launched this project, or it's in some development state yet? Or it's some history of... have you launched it like it was described?
Oh my God, thank you so much for asking, because it's actually available in our GitHub.
Yeah, but not implemented in which electronic cars, which...
no, there's an interesting economic question around there. So who should do what? We have been discussing for the whole day, and we'll continue discussing on who is responsible for getting cool cryptography to practice. So should, for example, the same research team who came up with the cryptography also start a fleet tracking company? Or should we just find one who is willing to start installing the new zero-knowledge trackers? So the economics of pushing cryptography into large-scale practice is a lot of fun. So we haven't gotten there yet, but I have a dream. Because doing this project was a lot of fun, and Martin and me drove around Washington DC and demonstrated this at the Pentagon and all of that. So it was a really cool project with real world impact, obviously, yes. But we haven't yet made it.
So this requested 80% is not counted anyhow now in Estonia, yeah?
They changed, I think, the tracking law for EV subsidies.
I don't think there is the subsidy anymore.
There isn't an EV subsidy right now, so.
We have in Latvia, but we don't have some strict measurements, just only kilometers for kind of years.
So we've had a discussion, for example, for vehicle taxation in Estonia, that whether people who drive cars, who live outside of large cities, should be paying less tax, because that's the only way they get around with. Because in cities you got everything, you got buses, trams, whatever, but if you live like somewhere in the forest, you need a car. So it is punishing for them to have a car. So the idea of fitting all cars in Estonia with a GPS has been floated by some think tanks. So we think this way is better. But it's a bit of there's a jump to be made. Thank you, Martin, very much.
Thank you.